Give it a few minutes.
That's good.
Oh, sorry for being a bit late.
No, no, you're all good. You're all good. I think you actually went to see where you were or something. Sure.
You're here for you. Sorry for being a late.
Ian said he will not be here.
Yeah, plans.
Oh, we have a homework due tomorrow. So that should be postponed, right?
Yeah.
Oh, no. No, I don't postpone the homework for tomorrow because I think it's independent of what I'm doing. It is on the same topic, but you don't really need that. It's pretty much whatever you have already seen in eigenbasis, you should be able to do that. So, okay, so
That's number 9.
that's homework 8. So what it says here, which was due November 9th, Tuesday.
Yeah.
What is the date? Oh, no, so it is homework 9. then.
9.
Yeah, homework 9.
Yeah.
The homework 9. This is due. Today is 15, right? So it's 16, correct? 16, 17. Yes. Tuesday. Again, if you want, you can take extensions, but that's how this is. There'll be one more homework due probably the end of next week. Not next week, the last week of classes.
Yeah.
So that's what. And midterm 3, we decided that we're going to have it on November 18th, Thursday at 8. So this week we'll have a lot of 5 teams. Wow. Okay. Visible. So we want to do the problem of harmonic oscillator in mechanics. That's the idea. So let's see how we proceed. So what do we mean by harmonic oscillator? It is so
You have written harmonic mechanics.
yeah. So I think in my head I was thinking harmonic oscillator in quantum mechanics. So then I said, okay. Okay. Let's go. The harmonic oscillator in quantum mechanics, right? So so what is harmonic oscillator? What do you say?
The extension of the spring is proportional to the displacement.
Exactly, right?
Negatively proportional.
Yeah, with the negative sign in front of it. So one can say that force is equal to minus kx, right? And we can also say the energy, like usually we say force. So we are going to talk in 1 dimension, so no vectors. So this is minus kx, right? So that's your k is the spring constant, but we would also like to put this mass in the perspective, right? So there is this relation that force is dp by dt, the change in momentum with respect to time, and that's equal to negative gradient, which is in 1 dimension, there's a negative derivative with respect to x of energy, right? And what is energy? It is half kx squared. Right, that's the same statement. The derivative of this. So this is a potential energy, right? Derivative of potential energy is equal to the force. So the same. Right. So that's what we understand by harmonic oscillator. Any system that obeys this equation will be the harmonic oscillator. Let us quickly write the Hamiltonian for this. Hamiltonian will have 2 parameters, x and p. All classical mechanics, nothing, not gone to quantum yet. And this will be equal to p squared over 2m plus, so that's the kinetic energy, and plus half kx squared. That's your and since there is no time dependence in the system, the Hamiltonian is actually the energy. So in the physical sense, it is that energy. What are the Hamiltonian equations of motions? So Hamiltonian equations of motions are, there are 2 parameters, or the 2 dynamical variables, x and p. So each one gets an equation, right? dx by dt and dp by dt. And those are given by, this is partial derivative of the Hamiltonian with respect to momentum. That's your first equation. And this is negative partial derivative of the Hamiltonian with respect to x. So that's your, these are called the Hamiltonian equations of motion. So what is this equal to? This is derivative, a partial derivative of h with respect to p. There is only p is only here, so there are two p's. So that's p over m. Right. And this gives you that's equal to derivative with respect to x. So that's minus kx. It is consistent, right? So the first equation tells you that momentum is equal to m x by dt, basically mass times velocity if you want. And this implies that force, which is dt by dt, is equal to minus kx. And if you substitute this in here further, so this together gives you m d square x over dt square is equal to minus kx. Right? It is Newton's law. Okay. That's all. Good. Now we want to do quantum mechanics of the same system. And the way we will do quantum mechanics is that we keep everything the same. And that's the advantage of doing Hamiltonian mechanics is that most of these things will go into quantum mechanics also. So how do we do quantum mechanics? So it's quantum mechanics. It's pretty much you say that, so now there are two variables, right? X and P in the Hamiltonian. You require that, the following conditions: X comma X commutation has to be equal to 0. P comma P has to be equal to 0. And X comma P, this is the new thing, X comma P is equal to IH plus. And immediately we see that, oh, this doesn't work anymore because here all these were numbers, right? X and P, and now they do not work. So we have to be more creative. We will also require that because we would like to interpret eventually, we'll be comparing with experiments. So we also require that X dagger is equal to X and P dagger is equal to P. That means X and P are Hermitian. That's one. So that's how we go into quantum mechanics. So clearly we have seen that either matrices or operators, some form of operators are the way to proceed from here. Let's see how we can. One way to go is Schrodinger's equation, where we directly go into the Hamiltonian. So you go in there. Before that, let me maybe do a few things. So, yeah, just a few. Yeah, just a quick recap. When I say just a ket, I mean an arbitrary state in the system. Like the system could be in any state in the Hilbert space, we call it. This is an arbitrary state. When I say X prime of this arbitrary state. This will be the projection of that state in the basis of position, right? Prime, remember, what the eigenvalues of the operator. So X is the operator, X prime are the eigenvalues of this. These are the projections of this. So this is, we will call this the wave function, psi of X prime. So this is the components of that arbitrary state in the position basis. We will often call this wave function. And X prime basis. Clear? Similarly, I can project this in the momentum basis, and that will be the same wave function in the position. Sorry, momentum. Is that clear? Any confusions on the notations there?
Right side, I mean the ket option is blank in both. So it doesn't depend on this. I mean this ket.
Yeah.
Yeah, this is blank. Also, next one, this is blank.
Correct.
So does not wave function depend on what is on the right side?
It does, in the sense, okay, I should write something there, but I'm not writing it. It means that it is an arbitrary vector.
Okay.
That way, that's a notation. I mean, it's not mine, it's Dirac's notation that when it is empty, it means it's an arbitrary state. It's like saying when we say the position vector is R, right? It could be anywhere in the vector space.
I'm actually asking this question because in your function phi, you just only written X prime. So it's only dependent on X prime like this.
Correct.
Okay.
Because
this is the basis.
That's the basis. Yeah.
Good.
Right?
Yeah. Thank you.
Like this is an abstract vector. We don't try to specify anything there. It is something in the space. Because the moment I give it some meaning, the moment I write a variable, that means then it's in that basis. Right?
Yeah.
Right? Like it's like saying R is in rectangular coordinates, spherical coordinates, cylindrical coordinates. It's all the same, but they're in different parameters. Right? So same. Okay. So that's the notation. So let's start with the Hamiltonian. It is dependent on X and P, and this is equal to P squared over 2M plus half a X squared. Okay. In fact, I don't even have to write that form. So let's see what is want to do this, no, not this. Okay, let's postpone this for a moment. So let's actually do one more thing. Let's start with psi of X prime, which is basically X prime. So the same, I'm just copying that. But now I can put in a complete set into this. Remember, P is also a complete set. So introduce X prime, P prime, that's right, and I have to integrate this over dp prime. Is that clear what I did? What I've used the fact that dp prime is equal to 1. Right? That's a completeness relation. Any questions? Yeah. So that's equal to dp prime x prime p prime, and that's psi of p prime. That's the wave function in the position basis. That's the wave function in the momentum basis. And in between, there is something. And based, this doesn't completely imply this, but we have to go into uncertainty and do more things. But it is very indicative here that, oh, this is Fourier transform people. Right? Here, it is not a proof I'm making, but it is indicative here that, oh, x comma p could be exponential of I x prime p prime. Right? So the point is the projection of, so this is not a proof, but a suggestive relation, since we're not doing a complete quantum mechanics. We don't have the time to prove this, but this is equal to exponential of I x prime p prime. Okay, so that means that the projection of momentum basis on the position basis will have exponential, and basically it's a Fourier transform. So this is a Fourier transform of the other. Right? But there is something missing here. Phase, no, more than that. Is this dimensionally correct? Like, what are the dimensions of x and p? X times p, let's say, of angular momentum, right? Like, exponential always has to be, can you take the exponential of a dimensional quantity? Like, what is exponential of force, for example? Like exponential, any mathematical function, you always do take it for a number. So you have to get rid of the dimension. So you have to do 1 over it. So for dimensional reasons, you put an h bar there. So that's where quantum mechanics comes in. And that's a different, like here, I have jumped. Basically, I haven't proved or I haven't motivated this enough as to why that h bar suddenly showed up, right? So it can be actually shown in a much more better way that it is empirical. H bar just shows up and you experimentally fix it. So it is not that you prove that this is H bar. So there is, when you actually do this, one can show in very general that the Poisson bracket is a commutation relation and it is equated to H bar. So that's a whole, somewhere else one has to do that, but we will use this projection. So what we are saying, you can say that I have used a hypothesis, if you want, that the projection of the momentum operator on the momentum basis on the position basis is exponential. And that moment immediately gives me a structure here. That's psi of x prime equal to dp prime times exponential of I over r x prime is of psi of p. Reasonable? But yes,
Sure. Yeah, I have a question.
Yeah.
So for your wave function, the sine of x equals the projection of the x basis on some arbitrary vector. And then you put in the completeness relation, like in between those two brackets. Could you show me how or why?
So that's equivalent to, remember, let's put the other side. So think of there are two vectors A dotted with B in normal vectors, and this is the same as thing A dotted with I hat of J hat with B. Is that clear? What I mean by that? So this will be A dotted with I hat dotted with B plus A dotted with A hat. This is for two component basis. This is for a many component, in fact, infinite component basis. That's exactly what I did. A dotted with B. So this is A dotted with B here in this Hilbert space, if you want. That's the two-dimensional real space. And then I introduced a one in between, completeness relation, and projected it. Does that answer it?
Yes, thank you.
That's all. Doing. And then I'm saying that these projections are actually exponential. So that's an important thing there. So that has to be motivated separately. But let's use. Okay. Yeah. So using this, let's find out what is because I'm interested in writing the Hamiltonian. So Hamiltonian involves the momentum. So first, let's say what is x prime of x of this? Right? What will that be equal to? If x acts on x prime, what will it give?
X prime x, I mean,
X prime x. That's correct, because an operator acting on its eigenvector, these are its own eigenvector, right? It will give me an eigenvalue and eigenvector again.
Yeah.
Right. So it will give me x prime, and the right side. Okay. This should in principle be star because it's acting on the left side, but it's a Hermitian operator, so its eigenvalues are all real, right? So it doesn't matter whether it is acting on the left or right, it gives me the same. This is a number, so it can come out. So it's x prime times, and that's equal to x prime times psi. Okay, so that's a function, that's a eigenvalue. That's clear.
Yeah.
So that's good. But now we want to do a little more on that. We want to do x prime because Hamiltonian have momentum also, right? So x squared will be the same thing, but now we want to do momentum. How would you go about doing the moment? What is momentum acting on x prime?
You have to change the basis.
Change the basis, very good, right? We know only how to act P on the momentum basis. Got to change the basis. How do I change the basis? I introduce this, right? So this is equal to, I don't know how this acts, so I want to, I will make it, I'll introduce a momentum basis. So, right? we say this is x prime, p, I introduce a p prime and a p prime. And that's a complete set, so that's p prime. Clear? And now I know how to operate this. Oh, this is p prime. Right? So, and then the moment it acts on that, it comes out. So this is equal to p prime. P prime comes out. And then I have x prime, prime. Yeah.
Yeah.
Let's put in the numbers for a moment. Oh, sorry, expressions for a moment. So that's p prime. This is, we said, exponential of I over h bar times x prime p prime, and this is psi of p prime. All numbers now, right? The moment all the primes come in, they're all numbers. We can work with numbers. So it's only the operators we have difficulty with, but we will get used to it. Okay. That's not really a Fourier transform, that is a t prime showing up, right? So we want to get clever to handle this p prime. Notice that p prime is the same as derivative with respect to x prime. If I act on x prime on this, it will bring down a p prime. So let me write this as one more line. So this is p prime. And I want to invert this h bar over I. So it's h bar over I and d by dx prime of exponential and psi of p prime. This acts only on this x prime, so it doesn't matter whether I write parentheses or not. Right? And you see the structure, momentum is the derivative showing up now. Like that will play an important role. Clear of the trick that I made there? Yes.
The primes are the eigen
Values of the operator x,
Okay.
associated operator,
Yeah.
right? So primes are always numbers. This is not a number, this is an operator. Right? This cannot come out of this. But the moment I made this act on that, it became an eigenvalue, which is p prime, and then I can bring it up. Is that clear? So that's that idea. But now I can bring this out. This is an x prime and this integral is p prime. So I can actually bring this out. That's equal to h bar I by dx prime of p prime and this is the same trick we will play again and again whenever we want to deal with operator. Temporarily, we'll go into the actual explicit relations and then get back into operator form. That's your wave function, right? Fourier transform of the momentum is wave function. So that's your h bar over I prime of psi. Any questions here until now? Okay, so if that's the case, then we can do the same thing again for x squared. X prime of x squared will be nothing but first time apply, get out the x, second time again x prime. So it is just x prime squared psi of x prime. And question?
No, sorry.
And x prime of p square. Again, so once you have taken this out, again go through the whole process again. So this will be another operator that will come in. So I'll leave that up to you guys. I'll not go through the details. This is p by dx prime square. And that's how you typically do, right? I mean, this is how Schrodinger equation is done. Wherever this operator is, replace it with x itself. P, you replace it with h bar over. So that's the guideline for going with the Schrodinger equation. So what is Schrodinger equation? Let's do that. Erase this. So what is Hamiltonian? So Hamiltonian is equal to p square over 2m plus half a x squared. Take the project this on an arbitrary vector and then project it on the x prime. That's equal to this one we said is h bar over I, because that will be the same idea there. X squared of x squared, x prime squared. So this is x prime, no. X prime squared prime psi of prime. If we connect this with energy, that's a Schrodinger equation. And if we say that if we look for, so what Schrodinger equation says is that this, I mean, look for those wave functions. So this is Schrodinger equation, right? So require this to be, look for those wave functions which are exactly eigenvalues of this. This is an arbitrary wave function. Find those wave functions which actually give me a number times this. And those are energy wave functions. And that's what Schrodinger equation looks for. And then the equation is e by dx square of kx square. If you solve this differential equation, if we solve this differential equation, that gives you your energy wave functions, and that's Schrodinger equation. Yes,
so the second line, how to do? I mean, left hand side and right hand side. How do we?
Oh, what I did is I did this on the left hand side, and I did the same thing on the right hand side, and used this. That clear? No.
You're just missing it 1/2m.
Oh, 1/2. Maybe I'm missing. Okay, let's do this slowly then. So this is the same as x prime p squared over 2m. Is this clear?
Yeah, not clear.
Like we say x squared. And that's the same as I have put the 2 over m.
Let's get out.
Let me squeeze that in here. 1 over 2m. Plus. Did that help?
Yeah.
5x prime. And that should show 1 over 2m here. Good. That's Schrodinger way of doing it. We want to, so, and there what you do is then you solve the differential equation. We are going to not do this. We are going to use some algebraic way of doing it, which is kind of neat, but no differential equation, but we'll reach the same state in a roundabout manner. Okay. So this probably from this point on, you have seen this in some undergraduate quantum mechanics course. Okay. Okay, so, and what are the solutions? What are the energy solutions for harmonic oscillator? What are they called?
H bar omega.
Those are the eigenvalues.
Sorry.
Eigenfunctions of Hamiltonian for harmonic oscillator. What are they called? Which special function is it?
Harmonic.
Not harmonic. Almost.
Harmonic.
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 Harmonic. Yeah, I think you meant it. Okay. So it is Hermite polynomials that are solutions. But let's go back to our Hamiltonian. And now, what are the Hamiltonian equations? And in operator form, Hamiltonian equations in quantum mechanics. It's almost the same. That's why Hamiltonian mechanics is nicer. dx by dt. This is still valid. Like even so, now these are operator. I am not writing primes. These are operator. This is still valid. Derivative with respect to that operator. In fact, this is also equal to 1 over IH bar of x comma h. So let's see. I should get back this P over M, right? If this is really true. So let's do this commutational relation. 1 over IH bar of x comma Hamiltonian is P squared over 2M plus half kx squared. And what is that equal to? So that is, this is equal to 1 over 2m comes out 1 over IH bar and x comma p square. And x comma x square, what is the commutational relation of x and x square? Is x comma x square. Zero, right? Zero, because x comma x, any operator x comma a times b is equal to x comma a times b plus a times x comma b. But we said x and x commute, we said, right? So this goes away. And this goes into 2x comma p, right? X comma p is nothing but IH bar. So this is nothing but 1 over 2m, 1 over IH bar, x comma p times p plus 1 over 2m, 1 over IH bar, p times x comma p. X comma p is nothing but IH bar. So this is equal to p over m. Indeed, exactly like earlier. we had this is equal to P M. But now these are operators. That's the difference now is that P and X here are operators. So they should be treated like operators. But so this gives the same thing, but it works out pretty much the same manner. Okay, yeah. Let's do the same thing with dp by dt also. dp by dt is equal to minus derivative of the Hamiltonian with respect to x. That will be equal to 1 over ix bar, comma. In fact, this is always true. Derivative of any operator with respect to time is a commutation relation of that operator with the Hamiltonian. So the time evolution is governed by the Hamiltonian. So this is in a sense a calculus, like you can show this in detail that, so this is a calculus like derivative. So there's a time evolution. So this is always comes out as a, for example, it doesn't have to be time. You might be interested in a variation with some other parameter like rotation. If it is rotation, this will come out to be the angular momentum. If it is derivative with respect to x, that's translation, this will come out to be the momentum. So as a general statement you can make, but those are, one has to do that in detail. There's a lot of work, time you have to spend on that. But you'll see that somewhere else in another context. Okay, so that's equal to the same idea again. H bar P comma P squared over 2m plus half K x squared. Again, P comma P squared goes away, that's 0. So that's equal to 1 by 2 K 1 over IH bar times P comma x squared. That's 1 by 2. So it is the same K and X. So 2 goes away. So K 1 over IH bar times P comma X times X. X comma P is 1. So P comma X is minus 1. So that's minus KX. In an operator form now. Okay, so that's just for completeness. So we have Schrodinger equation, which is basically the energy statement. We have linear set of equations, the usual Hamiltonian equations. That also goes through. This is how it looks like. And now let's go back to our Hamiltonian in an operation form. And let's, at this stage, let's now do whatever you're interested in, that this abstract description of harmonic oscillator. Meanwhile, if you have any questions, this is the time. Let's see now. So let's, yeah, h of x comma p. This is the same as p squared 2m plus half of kx squared. X and p are operators at this stage. And the same commutation relation. There is m and k are playing innocent roles here. Those are just dimensional quantities. Let us introduce like this is omega squared is equal to k over m. That's the time period, time frequency of the oscillator. Right. With that, let us define two operators, two new operators as linear combinations of this. And let us refer. So this is 1 over 2 h bar omega and square root of k x of I p over square root of n. That's one operator. And the second one will be y dagger, right?
It is minus.
Yes, exactly. That will be minus. That's one. Many of the books that I have seen, they use A and A dagger for this. But I use Y and Y dagger because I'm following Schwinger's book, so he uses it. So I'm just using it. Okay. So it's typically in literature you will call this A. By literature, I mean many of the books use A and A dagger. That's okay. So if that's the case, we would like to write. So now we have introduced two new operators for this. Then I would like to write my Hamiltonian in terms of this. Right? So I would like to solve for this, right? So let's add these two equations. If I add this, so I have y. So x becomes, so y plus y dagger is 2 times this, right? So it is 2 times h bar omega times 2 times square root of k. And that's y plus y dagger. But k is m omega square. Should I do that? Probably not. Seems to be okay with this. Okay. Actually, we should put this k on the left hand side. Square root of k. So that when we square this, we get this kx. And similarly, if I were to subtract these two quantities, right, if I subtract these two go away and they add up, right? So it is p over root 2m. So p over root 2m. And then I'll be dividing by 2i. So this is equal to 2 h bar omega and divided by, so it's y minus y dagger divided by 2i. So clear? Yes.
So y and y dagger, you just defined.
Oh, I just defined this. It's an observation you make that you define new operators y, which is this, and the dagger happens to be this. So instead of using, so there are two operators x and p, we will notice that there will be a significant simplification when we write it in terms of y and y dagger. But it's just two random operators.
Right.
That's all. And they are not Hermitian in the sense y is not the same as y dagger. So they are not Hermitian. So you don't want to make measurements on, like, or if you take a measurement, probably it's not physical. Yeah, it's not physical, but we will construct physical quantities. Okay. Clear? Okay, so what's our Hamiltonian in terms of this? I just try to square this, right? So Hamiltonian then is equal to p over I have 1/2 of square of this. So that's 2 h bar omega square of this. So that's 4, and that's I square is minus 1 of y minus y dagger and square. And plus half kx squared, so square this. So that's again 2 h bar omega over 4. Right. And that is y plus y dagger. So there is, how is this? So h bar omega 2 cancels, there is an h bar omega over 4 in both terms. And I can say this is y plus y dagger square minus of y minus y dagger square. Remember, these are operators, so I should keep my positions impacted. A plus b the whole square is not 2 times ab. I have to keep the order of a and b the same. So that's equal to h bar omega over 4. This is y squared. That order doesn't matter. That's y squared plus y dagger plus y dagger y plus y dagger squared and minus of y squared minus y dagger minus y dagger y plus y dagger squared. Clear? Notice that y squared cancels out, y dagger squared cancels out, and y dagger and y dagger y comes out with that factor of 2. Right. So our Hamiltonian in terms of this new, so that's a simplification that all of them and other things went away. So our Hamiltonian is in terms of y and y dagger is h bar omega over 2, because it was 4, but there's a factor of 2 coming up in all this. So this is y dagger plus y dagger. Like simplification in the expression for the Hamiltonian. And now that's our 2 parameters, y and y dagger. But can we do something with this? Earlier, when we wrote the Hamiltonian, we gave all this x comma x is what, x comma p is what, and x p comma p is what. But now it's the new operators. We should find all the commutation relations for this. So we ask, what is y comma y? At what will this be equal to? If y is equal to x plus ip, right, what will this be equal to?
0.
It should be 0, any operator when you, so this is y squared minus y squared, so that's 0. Y dagger, y similarly will be 0. So what about y comma y? That's the, since we know that commutation relation for x comma p, we can get that. So y comma y dagger, that is surely 1 over 2 h bar omega. That's going to be sitting there, and this will be so there is k times commutation of x comma x, right, because there is 2 of this. And there is x comma p, so this is minus I k over m And then there is x comma p. You see what I'm doing? That's basically putting together other things. So that's plus I k over m. And then I have p over p comma x. And finally, that's plus 1 over m p comma p. This is surely 0. This is surely 0, p comma p, and this is x comma p. I can change the direction. K over m we said was omega squared.
Yeah.
Right. So let's do all this. So this is 1 over 2 h bar omega minus I omega basically omega x comma p. And the same thing 2 times that, right? Because that will make this, right? That's what this. So what is that? All this equal to? Yeah, x comma p is, yeah, let's do this one more step. And yeah. So 1 over 2 h bar omega. That is minus I omega. This is I h bar, and that is a factor of 2, right? I's go away, h bar omega goes away, so this is equal to 1. So, overall, what we have said is that, or actually, let's do one more thing. So this means that y dagger minus y dagger y is equal to 1, correct? But inside I can actually replace that, go back and replace that. So the Hamiltonian is equal to h bar omega over 2. Y dagger is y dagger y plus 1, and there's already a y dagger y. That's h bar omega over 2 times y dagger y plus 1. And that's the same as h bar omega times y dagger y plus half. So overall, if we now switch over to y and y dagger completely for a moment, what's our harmonic oscillator problem? So harmonic oscillator problem is h, which is a function of y and y dagger operators, y and y dagger, is equal to h bar omega. That's the dimension of energy, and y dagger y plus half. And I have to specify what's the commutation relations. So y comma y dagger is equal to 1, y is equal to 0, and y dagger is equal to 0. So that's our harmonic oscillator, right, in terms of y and y. And that will be our starting point in a sense. So basically, we rewrote our whole Hamiltonian, which was in position and momentum, in terms of 2 operators. But once I do all those definitions, this is my fresh start. Y dagger y, this is my commutation relation, and everything is contained in this. I don't have to go back now. We will go back here and there, but that's a exactly same problem written in another basis if you want. another operators. Okay. Any questions at this stage? Yes.
You said that these Hamiltonians are equivalent.
Equivalent, exactly. They are identical in the sense that it's a transformation, right? If I do this, I get here, right? If I start from here, I can go there. Right? So either I say my Hamiltonian is this with x comma p equal to ih bar and so on, or I say it is this with these commutation relation, one-to-one relation or identical actually, mathematically identical. Here.
Yes. And our new basis has different properties.
Correct.
Than our
Exactly.
previous.
Exactly.
Okay.
Exactly. And that will be our advantage. Right? Like this will, yeah. So this will, like this will let us go from one basis to the other more easily. Like there is this idea of raising operator. Have you guys seen this?
Ladder operator.
Ladder operators. Yeah. So we will be able to go from one to the other in a nice way. And so basically the idea is if you get the ground state, which is the bottommost state, then each one we will be able to keep just using a prescription. We will be able to do. Otherwise, we were using the idea of differential equations to get all those eigenfunctions. Here we will solve for the ground state and then just get them exactly, get them symbolically, and whenever needed, we can put a wave function to it. Okay, so that's the idea. Okay, clear? Okay. So let's construct a little more, and then I will. If that's 6 o'clock, so I can take 15 more minutes, maybe 10 or 15 more minutes, and then I'll stop. Okay. So we need to have some basis, correct? So I already have y. I can have y basis. I can have y dagger basis, but y and y dagger are not Hermitian, so they're not very convenient bases. So I would like to have a basis of Hermitian operators, and in this place, I have 3 operators, right? Y, y dagger, and h. That's the only 3 operators I have. Yes.
So y is also an operator.
Y is an operator.
Also, you are using y can be a basis.
Y can be a basis, but I'm not going to use it because it is not Hermitian.
So an operator can be also a basis.
No, operator by basis, what I mean is that y prime is equal to y times y, right? Find the eigenvalues of the operator. The eigenvectors become the basis, right? So if the language is in the eigenbasis of y. Eigenbasis of y means the eigenvectors of y, which is y prime. I can use this as my basis. I can use this as my basis, y dagger prime is equal to y dagger prime. Or the third operator is the Hamiltonian. H and H prime is equal to prime, right? So yes. Oh, yes. Oh, is this slot occupied?
No,
Oh.
I was trying to turn the review thing in, but I think the office is locked.
Oh, maybe what you could do is. Yeah.
In the last semester, you were TA. Last semester, you were TA.
Yeah.
So do I need to submit the evaluation myself, or how the?
Yeah, you want someone else to go there. So have a student in your lab,
Mhm.
turn it out for you.
Okay.
You're not allowed to type it out.
Okay, got it.
Okay. Yeah, so I guess that's what they mean when they say eigenbasis, right?
Correct.
Because it has to be from the eigenvector.
From the eigenvectors. All the eigenvectors, take any operator in the system, and the eigenvectors of that operator form a complete set. Always. And you can work with that. momentum is so we used momentum, right? P prime when we said that was an eigenbasis of momentum. Eigenbasis of position, eigenbasis of Hamiltonian. Eigenbasis of Hamiltonian is very, very special because that's what we always measure. Energy is what is measured in most of quantum experiments. And that's what Schrodinger equation does. So Schrodinger equation does this very specific thing that experiments are done in energy. Let's go and manually do this for energy. But this is more abstract. We are able to go from one to the other. And this has much more flexibility in analyzing, not an experimental point of view, from a theoretical point of view, what we mean, what is a calculus in quantum mechanics, what is derivative, what is variation. Like when we do a calculus, we need to change the operator. What do I mean by that here? So those things you can work in this figure. Like that, there's much more, or whatever you think you can actually do in this. Schrodinger equation is very limited. But it's nothing wrong in Schrodinger equation. If you know what you're doing, then Schrodinger equation is good. Okay. Clear? Okay, so we need the basis now, right? And notice that this 1/2 is just innocent there, right? This y dagger y. So we need a basis. We will have an operator called n. It is y dagger y alone. Basically, forget the units, forget the half. So this y dagger y. So that's an operator now. N is an operator. Okay. Once it's an operator, I can look for the eigenbasis of that operator. So I construct my eigenbasis as n prime is equal to n prime. And I don't know what these n primes are. I don't know the eigenvalues yet, right? I have only written down the operator, but I haven't solved for the eigenvalues yet. But we will see what these it will come out in a sense. Okay, so we should know that eventually our goal will be. So this is the construction of the problem, if you want. I write the operator in very abstract form, and I build this. But to be able to do experiments, what should I know? I should know the eigenvalues, right? I should know not n prime. N prime is not that important. I need to know its projection in position. N prime projected on the position, because position is what we do. You do it in the lab, right? So you need the position. That becomes your waveform. Those are your two questions you would like to ask. Right? And of course, energy. Once you know this, then you can get the energy. But those are the two primary things. What are the eigenvalues, and what is the projection of this particular eigenbasis, whichever you like, you preferred this. What is it in the position? What's the projection of it in the position?
I also can project it into momentum basis.
You can do it in a momentum basis. Typically, we do this. Yeah. So once we know this, then you can do this in momentum. Of course, energy, everything you can do. But typically, these two are the primary goals of the problem. Clear?
I'm trying to actually select what you're doing. So if I have an operator, so I can actually get the eigenvector of the operator and the eigenvalue.
Correct.
Okay, so even if I don't know the eigenvector, I can project it into a particular basis.
Correct.
So it's not compulsory for me that I need to know the eigenvector.
Don't need. Yeah. Whichever eigenvectors you know, project it onto that. You need to know for one, at least for one operator you need to know. And another thing that will come up here, it is very simple. There is only one that is not commuting, right? There is one thing that you learn is that if you project it in one, like already we talked about that, right? If they are conjugate variables, if I project it into one, and then again I project into two, I forget that, I lose my memory. Right? So those things are all inbuilt in this. So those challenges are there. But otherwise, mathematically speaking, we're just interested in you get me one eigenset or one eigenvalues, and then I'll keep projecting onto that. Okay. So these are my. So I will be looking for these two. Right. So let's see, and I don't even know what are the n primes, like I don't know the eigenvalues. So if I know this, pretending that this equation is known, in this eigenbasis, what is Hamiltonian? So let's see. So Hamiltonian is equal to h bar omega. Notice n without a prime is operator, so it is n plus half. Right? But it's an operator. This and immediately I know that h acting on n prime will be equal to h bar omega n prime half. Now it's number and n prime. We can ask at this point, what is this n prime? Is it complex? Is it real? Is it something else? What is it? Is it negative, positive? We can ask that. And we go back here, right? Notice y and y dagger are not Hermitian. But is n Hermitian? N, is it Hermitian? So n dagger is equal to y dagger, y dagger. And that's equal to y dagger, y, which is n. So that's real. N is real. Or n prime is, if n is Hermitian, then n prime is, n cannot be real, that's it. Questions?
Yes. So y dagger y raised to the dagger is still y dagger y.
Yeah, because
Yeah.
AB dagger is, this is a transpose, right? So this is B dagger times B dagger.
Oh, the train. Yeah. Okay.
Right,
I forgot the
so that is a
train.
transpose and then,
Conjugate transpose.
yeah, conjugate transpose that flips the order of multiplication. Oh, forgot. Okay. So now what we have is we haven't made much progress. We said this is a Hamiltonian, that's your definition. So we are interested in this n prime. The only thing we have made progress is that there are lots of eigenvalues and they're real. So hardly any progress. All right. So, but let's see what we can do. Okay. Now let's say that, what about let's say y times y prime is equal to y prime. Right. So basically there is an eigenbasis in that. Right. So what about y? Y is not Hermitian, but its eigenvalue is y prime, right? So n, like when built out of eigenvalues, n prime would be equal to, let me put it this way. So y dagger acting on, I'll put it like this. I start with this equation and take a complex conjugate. So then I get y prime, y dagger equals y prime star. which means to say that the eigenvalue of y dagger is the complex conjugate of the eigenvalue of y. Right? Y and y dagger have complex conjugates as eigenvalues. Okay. So if I know that, then in terms of this, I can say n prime would be equal to y prime star times y prime. Maybe I should show that more explicitly. Let's start with n and operate this on y prime on the left and y prime on the right. Okay, I can always do that. That's equal to y prime, y dagger, y prime, which is the same as y prime star times y prime, right? Because y prime. So whatever n is, so this implies what we are saying is that, so notice that this is now greater than or equal to 0. Because this is a magnitude now, right? This is an absolute value. This is a star and a complex number with a complex conjugate that's greater than or equal to 0. So so this implies that n prime, the eigenvalues that we are looking for, is not just real, it is actually greater than or equal to 0. So we have made a little more progress, that we have argued that it is actually real, but now it is actually non-negative. So these are n prime. So this implies that n prime are non-negative.
Yeah, I'm sorry. Why is the why is it greater than or equal to 0? I think I missed.
Yes. So,
Star y.
okay, this is an operator. Think of the following. Okay, typically this is, I think we used this somewhere else earlier. I think that's the better way of doing it, instead of, because in this equation you will argue that, oh, this is not really n, right? So look for a matrix. Let us say that there is a matrix A raised to q is equal to 1. What are its eigenvalues?
I'm sorry, you're saying
Eigenvalues of A.
where a cubed is equal to 1.
There is a matrix whose cube is equal to 1. That's the only information you have. Okay. But then you ask, what are the eigenvalues of that matrix? Okay. And the statement is that you can diagonalize this. Okay. So diagonal matrix also satisfies the same, or for that matter, that eigenvalues, let's say eigenvalues of A is A prime. A prime cube is also equal to 1. Always. So that's an algebraic equation. That's a polynomial equation. So the complex unity, 3 roots of unity comes into picture. So, so this is your 1. That's your 3 roots in the complex length, right? So my point is that if you have a matrix, if you have an operator equation, eigenvalues satisfy exactly the same equation. Okay. Any operator, put in the eigenvalues and they will satisfy the same equation. Okay. So here we have n is equal to, so simple way of looking at it is that n is equal to y dagger y. It's built out of 2 operators. If I were to take this into the eigenvalue sense, n prime is equal to y prime y star. That has to be true. And you will show it using these methods, but if you just use that as a statement, that's sufficient. And because this has this construction of y and y dagger, it always has to be greater than or equal to 0. All the eigenvalues. Is that clear?
Yeah.
That's the way of perfect. So this implies this. So I don't have to go through all that. But I was trying to go through all steps so that I don't have to say that I didn't want to use a theorem as such. This is called it as a name associated with this theorem. Cayley-Hamilton theorem. I think it's pretty straightforward. Often people say that, oh, why should you give it a name? Cayley, I think Cayley, Y or I?
Y.
Y, Cayley, Hamilton. Yeah. It's pretty straightforward if you think about it. You just diagonalize it and it works out well. So often people say, oh, there is no need to give credit to anyone. Everyone probably knew it. But then I don't know. Okay, clear. So only tiny development made. We have said that we were looking for eigenvalues. We have said that they are non-negative. That's it, right? And they're real, non-negative and real. And let's stop here, and we will come back to this. And so now we will begin from here. Okay? We'll begin from here, and we'll use this n prime, and we will show first that what is the role of y. Y actually goes down and y dagger actually goes up. So yeah, these are ladder operations. And very quickly you can build the whole operations in this. And very geometrically or algebraically you can solve the whole harmonic oscillator problem. But you've seen this